Morning or afternoon, everyone. Welcome. Today, I'll be talking about edge-ready GenAI, optimizing performance and efficiency for resource-constrained environments. As generative AI continues to evolve, deploying these powerful models directly on edge devices like smartphones, sensors, or embedded systems presents unique challenges but also incredible opportunities. We'll explore practical techniques like quantization, pruning, and knowledge distillation to make GenAI feasible and efficient right where the data is generated, without constant reliance on the cloud. I'm excited to share these insights with you in this talk today. Just a little bit about myself. My name is Kalyan Reddy Pentaparthi. I work as Principal Software Engineer at ST Engineering iDirect. Feel free to connect with me on LinkedIn. My work primarily focuses on global connectivity through IP satellite network infrastructure. Edge plays a critical role in this platform, like satellite VSAT terminals on airplanes, ships, cruises, remote geographical areas, etc. And connecting back to the cloud for us is very expensive because it utilizes that expensive satellite bandwidth. Why is Edge AI deployment so challenging? We are operating at the edge computing frontier, which is fundamentally different from the cloud. First, limited computational resources. Edge devices simply don't have the processing power, memory, and storage capacity of data centers. Second, energy constraints. Many devices run on batteries or have strict power budgets, limiting how complex our AI models can be. Third, connectivity challenges. Reliable internet access isn't always guaranteed at the edge. Our AI needs to function even with intermittent or no connection. Finally, real time requirements. Many edge applications, like autonomous systems or interactive assistants, demand near instant responses, putting immense pressure on model performance. These constraints shape how we approach building AI for the edge. Here, under these constraints, edge ready Gen AI needs to be built on solid foundation. This means focusing on four core principles during inference stage, which is the stage where the model makes the predictions. First, optimized performance. We need real time inference with minimal latency. Second, energy efficiency. Minimizing power consumption is critical, especially for battery powered devices, without crippling the model's capabilities. That's a very delicate balance. Third, resource awareness. Models must be adapted to work within the tighter memory and processing limits of edge hardware. And fourth, architectural flexibility. Our solutions need to support diverse hardware environments and various use cases. The optimization framework we'll discuss aims to address all these principles simultaneously. Powering edge AI often requires specialized hardware, frequently referred to as edge GPUs or accelerators. This table gives a snapshot of the landscape, comparing key players like NVIDIA Jetson series, like Orion Nano, NX, AGX, their RTX embedded line, AMD's Ryzen AI with NPUs, Intel's Core Ultra with NPUs and Arc GPUs, Google's Coral TPUs, Qualcomm, Snapdragon NPU, and specialized players like Edge Cortex. Notice the diversity in accelerators GPUs, like GPUs, NPUs, TPUs, and the wide range in the AI performance. Like AI performance is usually measured in tops or T flops. And also look at the memory capacity and bandwidth, and crucially, the power consumption, which is measured in the form of TDP. Selecting the right hardware involves balancing these specs against application needs and device constraints. Now, how do these accelerators actually perform when when running large language models like Llama, or Mistral. This table attempts to capture some illustrative performance data, but honestly, direct standardized comparisons across all these edge platforms are still hard to come by. Performance depends heavily on specific model, the level of optimization, especially the quantization, like is it using int4 parameters or integer 8 parameters, and the software framework used, like NVIDIA's TensorRT LLM or ONNX runtime. Also, key metrics to watch are throughput, measured in the form of tokens per second, and latency, time to first token and inter token latency. As you can see, many entries still show the data needed, highlighting the need for more rigorous cross platform benchmarking in this rapidly evolving space. Hardware is only half the story. The software ecosystem is equally critical. We rely on key AI frameworks like TensorFlow Lite and PyTorch Mobile, which are adapted for edge deployment. Beneath them are inference optimization engines like NVIDIA TensorRT LLM, ONNX runtime, which is cross-platform, and Intel's OpenVINO and IPEX LLM. These engines apply crucial optimizations to make models run fast. Finally, the vendor-specific software stacks like NVIDIA Jetpack, AMD Ryzen AI software, Intel One API, and Qualcomm AI Stack provides the drivers, libraries, and the tools needed to fully leverage the underlying hardware. A mature and well optimized software stack is essential to bridge the gap between the model and the metal. Given these resource constraints, we can't just run large off the shelf language models on the edge devices. Aggressive optimization is mandatory. There are several techniques, but today we'll focus on the top three most impactful ones for edge deployment. First, the quantization, which is arguably the most crucial technique. Second, the network pruning. And third, knowledge distillation. We'll briefly touch upon others like low rank approximation and memory optimizations, but these top three form the core of making LLMs edge ready. Let's start with quantization. At its core, quantization reduces the numerical precision used to represent the model weights and sometimes activations. Instead of using the standard 32-bit floating point numbers, we'll convert them to lower precision formats like 16-bit floating point numbers or even 8-bit or 4-bit integers. This dramatically reduces the model's memory footprint and bandwidth requirements, making it ideal for the edge, and also speed up the computation if the hardware has support for these lower precisions. The main approaches are inside the quantization are post-training quantization, quantization-aware training, and also dynamic range quantization. First up is this post-training quantization. As the name suggests, you take a predefined floating point 32 model and convert its weights to a lower precision after training is complete. The big pros are its simplicity and speed. There's a minimal development effort and no need for retraining. However, the main con is that it can lead to moderate loss in model's accuracy compared to that original floating point 32 model. Because although often this degradation is less than 2% for conversion to integer 8 format. It usually requires a small calibration dataset to determine the optimal quantization parameters for us to determine which precision works better. PTQ is often the first technique tried due to its ease of implementation, actually. Why is this quantization, especially to integer formats like int8, so effective? Uh, this is the spec sheet for NVIDIA 810 GPU, which illustrates it well. Look at the performance figure for standard 32-bit floating point operations. It achieves about 31 teraflops. But for 8-bit operations, 8-bit integer operations, it jumps to 250 tera operations per second, or even 500 if sparsity is leveraged. That's roughly an 8x to 16x increase in theoretical throughput. Modern GPUs and NPUs often have specialized hardware units like NVIDIA's Tensor cores designed to accelerate these low precision integer calculations, turning memory savings from quantization into significant speedups, actually. Next technique is quantization aware training. Here we simulate the effects of quantization during the model's training or fine tuning process. The model especially learns to compensate for the precision loss. The main pro is that QAT generally achieves better accuracy prevention compared to PTQ, often with less than 1.5 degradation for percent degradation for integer 8 conversions. The cons, it's more complex to implement, requires access to the original data, training data, and pipeline, and involves longer training times. QAT is preferred method when accuracy is paramount and the cost of retraining is acceptable in some use cases. Next is this dynamic range quantization. This offers a balance. Instead of using fixed quantization parameters uh, determined offline like basic PTQ, it's adaptively adjusts these parameters based on statistical properties, the range of activation values encountered during the inference. Its pros are that it often strikes as a good balance between the accuracy of QAT and simplicity of PTQ, and it adapts better to varying input characteristics. It can also reduce memory bandwidth requirements. The main con is the potential for some runtime overhead due to this dynamic calculation during the inference stage, which might increase the computation footprint of the edge deployed models. Finally, this mixed precision quantization, this recognizes that not all parts of neural network are equally sensitive to the precision. This technique uses different precision levels for different layers in the neural network. For example, more sensitive layers might be kept at FP3016 or FP32, while less sensitive layers are quantized more aggressively to int8 or int4 weights. The pros are that it balances compression and accuracy effectively, allowing higher precision where needed. The cons are that it requires careful analysis to identify which are sensitive layers and often needs specific framework and hardware support. Done well, it can achieve significant compression, like some cases like 70%, with minimal accuracy loss, less than 1%. See, it's all about the balance, how accurate you want your model to be and how uh, performance efficient your model has to be. So, next LLM automation technique I want to discuss is this neural network pruning. Uh, the idea here is that large neural networks are often over parameterized, meaning they contain many parameters, that is, weights or connections that aren't essential for their performance. Pruning systematically identifies and removes these redundant elements. The process involves analysis to find non essential parts, targeted removal of these parts, and then fine tuning them into the smaller prune network to recover any potential losses. Pruning can dramatically reduce model size, sometimes by up to 90%, with minimal impact on accuracy, making models much smaller and faster for edge deployments. Let's look at the general pruning process in a bit more detail. Step one is to train the initial potentially over-parameterized network until it converges. Step two is crucial part, identifying and removing unimportant elements. This involves applying some criteria or heuristic to determine which weights, neurons, or even larger structures to prune. Once identified, these elements are removed, often by setting their weights to zero or removing entire structures. Step three is typically fine tuning the now smaller prune network for few epochs. This allows the remaining weights to adapt and help recover most, if not all, of the original accuracy. How do we decide what to prune? The simplest and most common approach is magnitude based pruning. It operates on assumption that the parameters with small absolute values contribute less to neural network's output. Weight pruning, unstructured, removes individual weights below a certain magnitude threshold. This results in sparse, irregular matrices offering higher compression potential, but are often requiring special hardware or libraries for speedups. Unit neuron or filter pruning, like a more structured way, removes entire structures like neuron or filters based on an aggregate score such as L1 or L2 norm of their weights, normalized weights. This results in smaller dense matrices, which essentially leads to easier inference speedups on standardized hardware. Through the though the granularity is much coarser. Beyond just magnitude, importance-based pruning uses more sophisticated metrics like uh, to determine which elements to remove. Instead of just looking at the weight size, it might consider effective of removing an element on the model's loss function using techniques like Taylor expansion and other things. It can also analyze activation statistics like frequency or variance, or look at gradient information. The goal is a more sophisticated selection of elements, potentially leading to better accuracy for given level of sparsity compared to simple magnitude pruning, though it can be more complex to implement. So it's kind of like on one end we have a simple approach, and on the other end we have much more complex using much more mathematical functions to find which layers to prune. Pruning doesn't happen all at once. Iterative pruning, another technique, involves repeating the cycles of like prune, fine tune multiple times. In each iteration, a small percentage of weights are pruned, followed by a short period of fine tuning. The goal is to reach the target sparsity level gradually. The main benefit is that this iterative process often leads to better accuracy for a given amount of pruning compared to pruning everything in one shot. The trade off is that it's naturally more time consuming. I want to cover this too. This is a fascinating related concept which is called as a lottery ticket hypothesis. This suggests that a dense, randomly initialized networks contain sparse subnetworks, the winning tickets to call. If trained in isolation from the start using their original initializations, can match the performance of full dense network. Magnitude pruning is often used to uncover these small subnetworks after training that dense model. This hypothesis implements an inherent sparsity within the neural networks and provide a theoretical underpinning for why pruning can be so effective without sacrificing accuracy. It's all finding that subnetwork like which can be much more critical than the entire dense model. Next, the third key LLM optimization technique is knowledge distillation. Imagine you have a large, powerful teacher model, perhaps a state of art model running on the cloud. It has excellent accuracy, but it's too large and slow for the edge. Knowledge distillation allows us to train a much smaller, compact student model to mimic the behavior of this teacher. The knowledge transfer happens by using the teacher's output, often soft labels or probability distributions over classes, and sometimes it's internal feature representation to guide the student's training. The result is a student model optimized for the edge deployment that preserves key capabilities learned from the teacher, enabling edge deployment with efficient inference. See, on the edge, it's always about very specific tasks. So we have this big teacher model, training a smaller student model, which can be deployed at the edge. How is the knowledge actually transferred, like from the teacher to the student? We can categorize distillation based on the type of knowledge. First one is like response-based distillation. Focuses on matching the output layer predictions of the student to the teacher. Using to teacher's full probability distribution provides rich information that just the final predicted class needs. Other one is like feature-based distillation, which goes deeper, encouraging the students' intermediate layer activations or feature representation to become similar to teachers. This pushes the student to learn similar internal ways of processing information. Both approaches uh, have proven effective in significantly compressing models while retaining their performance based on the research. We can also classify distillation by training strategy. Offline distillation is the most common one. A pre-trained teacher model trains the students directly. Online distillation trains the teacher and students simultaneously, allowing them to learn collaboratively. Self distillation is interesting. A model distills the knowledge from itself, often with the deeper layers teaching shallower layers. That's very interesting. Progressive distillation uses intermediate teacher assistant models to bridge a larger gap between a very complex teacher and a very small student. These different strategies offer like a flexibility depending on the specific models and training setup. Okay, we have covered the core optimization techniques. How do we actually implement them? Several frameworks and uh, tools are already designed for this. Like TensorFlow Lite from Google is highly optimized for mobile and embedded devices, offering excellent quantization and model conversion tools, especially strong on Android with Google's HTPU hardware. ONNX runtime, another interesting one from Microsoft, is a versatile one, cross-platform inference engine. Its strength lies in using execution providers to target various hardware accelerators. It's more for cross compatibility across the hardwares. PyTorch Mobile provides an end to end workflow for deploying PyTorch models, supporting optimization and selective builds. Finally, the hardware accelerators like Google's HTPU or the Neural Engine NPUs integrated into processors from Apple, Intel, AMD, and Qualcomm often come with their own specialized optimization tools and software stacks to maximize the performance for their specific architectures. Does all this optimization actually work? Absolutely. This chart shows illustrative results before and after applying a combination of techniques like pruning and quantization. We see drastic improvements like model size reduced significantly, like 76%. Memory usage drops. Inference times measured in latency decreases substantially, like 70% in this example. And perhaps most critically for the edge, power usage plummets by 85%. These kinds of gains are what makes complex AI models viable on power constrained edge devices, turning theoretical probabilities into like practical applications. Let's look at some real world examples where these techniques make a difference, like embedded voice assistance, real time object detections, on edge language translation, and predictive maintenance. So, implementation roadmap, like if you have to develop this for our edge deployments, how do we do that? Here is what I suggest. First, audit model requirements. Thoroughly understand your target hardware constraints like memory, power, compute, and performance needs of your application. Second, prototype optimization pipeline. Test different techniques like quantization and pruning individually on your model to assess their impact and feasibility. Third, implement a combined approach. Integrate the most effective techniques sequentially, perhaps pruning first, then quantization, maybe followed by distillation if needed, validating carefully at each stage. Fourth, deploy and monitor. Like release your optimized model to the edge devices, but ensure you have telemetry and other monitoring in place to gather real world performance data, which can guide future improvements and updates. Here is the roadmap slide. I have compiled some very useful links and references from my research into a PDF and sharing the link here. For those who wants to dive deeper into these frameworks, techniques, and other references of the latest research papers in these areas discussed, and also a link for the slides of the talk. Thank you very much for your time and attention, everyone. And I hope this overview of optimizing generative AI for resource constrained edge environments was informative. And have a good day. Thank you.